Hello everybody and welcome to another video. Today, this is actually the first video in our series discussing partial differential equations. This is going to be a multi-video endeavor where we're going to be talking about some of the subjects such as these. Namely, we'll be talking about modeling engineering problems using partial differential equations. We'll talk about a few famous partial differential equations such as the 1 and 2D wave equations and heat equation. We'll also look at solutions of these equations using techniques such as the separation of variables. We'll also talk about eigenvalues and eigenfunctions of partial differential equations. We'll also talk about Fourier analysis, Bessel functions, and numerical solutions to partial differential equations. So if all of this sounds good, why don't we jump right in and talk about what is a partial differential equation. All right, so the easiest way to start talking about partial differential equations is to actually back up a little bit and remember our discussion on ordinary differential equations. So if you remember here, our idea with ordinary differential equations, or let's just refer to these as ODEs so we don't have to keep writing that out here, is the idea with an ODE is you might have some function, let's call it u, and this might be a function of one independent variable t here. And this differential equation that describes how this function evolves here might involve derivatives of this function. So in other words, you might have something like, you might have the second derivative of this function with respect to the independent variable t in this case. And then maybe that's added to, I don't know, the first derivative of that function with respect to time, plus maybe the function itself here, right? U of t here, right? And this might even equal some external forcing function. Let's call it maybe f of t here. And you know what? All of these terms, the function itself, its derivative, its second derivative, they might have constants in front of it like an a b, and a c, these coefficients. And finally, with this ordinary differential equation, you might have some initial conditions associated with this. If you remember our lecture earlier, we discussed that with a second order differential equation, you actually need two initial conditions to fully satisfy this. So you might say that this problem also comes along with this function at a certain time, like usually time 0 is the easiest spot, is equal to some value, and maybe its first derivative here, or u dot at that same time, is equal to some other value here. So this is our typical format of an ordinary differential equation. This might be used to describe something like the deflection of a block. All right, you might have some mass here attached to a spring and a damper. And I think you've all seen the situation where if I want to measure the deflection, let's call it u, as this block moves up and down, this differential equation might describe that motion here, right? So the idea with an ordinary differential equation here, in fact, this one is actually linear in this case here, but the concept with this differential equation is that we are trying to find this function u of t here, right? This is equal to something. Some function, but the key here is that there's one independent variable, right? Time is the only independent variable. If you know what this function is as a function of time, that will describe how does this block move up and down at any given point in time, all right? So the goal with solving this ordinary differential equation, again, was just find this function u. Now, what if instead of just this single point here, like a single mass that's moving up and down, what if we had like something more complicated? So for example, let's say you had a continuous string or rope. Maybe it looks, I don't know what it actually looks like. I'm going to draw it kind of in some exaggerated fashion. Maybe this thing has length L here. So let's draw x maybe as the this x-axis here, and then the vertical thing is still u. Maybe the deflection of how much has this string moved away from this x-axis here, right? So now in this case, we see that if I also want to describe the deflection of this string, so if I want u to describe the deflection of string, we see now in this case, as this string moves up and down, you see it's actually a function of two variables. It's a function of when you look at the string, and it also is a function of where along the x-axis or this spatial variable do you look at it? So now u is actually a function of time and space. So there are two independent variables, right? So in this case, you have two independent variables. You've got t here, which is time here, and x here, which is some sort of, I guess we can call it space, right? Because it's some spatial location here at an x distance here. So in this case, the deflection of this string is not going to be governed by an ordinary differential equation. I need to find this function u, which is a function of two independent variables, and that's what makes this a partial differential equation. So let's just go ahead and write that down here. And in order to, again, avoid writing the words partial differential equation over and over and over, let's just call these things PDEs from here on out, okay? So a partial differential equation, or a PDE, is basically an equation involving one or more derivatives or partial derivatives of an unknown function of two or more independent variables. So let's just write that down here, right? So this is an equation involving one or more partial derivatives of an unknown function of two or more independent variables. Okay? And the other thing that's kind of key to look at here is now we have this word partial derivative, right? Earlier in the ordinary differential equation, we were able to just use, oh, whoops, sorry, gosh, back here I missed a d here. Whoops. Sorry, I should have had a d over there in my differential equation expression. But anyway, these were d's, right? Because there's only one independent variable, so you can only take a derivative with respect to one variable here. But now we have a partial here, so instead of using the d terminology, we're going to start using the partial terminology here, right? To determine which variable are you taking a derivative with respect to, okay? So, one other thing that we may want to talk about right now here is let's talk about the order of a given partial differential equation. So the order of a PDE is the order of the highest derivative of whichever partial shows up in the equation. And we'll look at an example here in a second, but maybe let's just go ahead and write that down here. So the order of the highest derivative okay, is called the order of the equation. Okay, so let's take a gander at what a general form of a PDE might look like. So let's go ahead and maybe let's leave our ODE up here, and we'll go ahead and erase some of this down below and just write out a general form of a partial differential equation here. So in general, we saw that this partial differential equation, let's just write that as PDE, like a general format. Okay, so we saw that this function, let's call it maybe big F here, right? This is going to involve potentially more than one independent variable. So you could have an x1, an x2, all the way up to an xn. So these are independent variables. So it could be time, space, whatever the independent variables here for your expression here, right? But now what makes this interesting here is that we're again looking for this function u, but the u could now be dependent on all of these as well as their partial derivatives. So you might have the partial derivative of u with respect to the first independent variable x1. You might have the partial derivative of u with respect to the second independent variable, etc., all the way up to the partial derivative with respect to the nth here, right? And you know what? You don't have to stop at the first derivatives, right? This equation might have second derivatives. It might have mixed partials. So to keep this general, right, you might have something like partial squared u with respect to x1 and then with respect to x2, right? And you see you can start mixing all of these partials up as much as you like to get all of these different terms in here. And then maybe we'll just leave it as that. Like this is a general expression, right? And this might equal I don't know, 0 or something like that, right? It might equal some forcing function, but you could always subsume that forcing function over here. So in general, this is sort of a very open-ended way that you might go ahead and define a partial differential equation. So partial differential equations, we're going to see, can be used to actually describe a wide variety of engineering and physical phenomena such as sound, heat, electronics, things like that. Why don't we go over to PowerPoint real quick, and I'll show you a couple movies of some example PDEs, particularly ones that we might take a look at here during the course of this lecture.
So I wanted to give a couple examples of some systems that are modeled by partial differential equations. So one example here is a vibration of a string. So we're actually going to take a look at this in a little bit, and this is what's known as the 1D wave equation. We'll also see that you can extend this idea to multiple dimensions. So in other words, you could have a vibration of, instead of just a simple string, you could have a vibration of a two-dimensional plate. Another place where we see partial differentials in engineering is things like the diffusion of heat. So we'll take a look at a system where you've got some heat distributed in some fashion, and we'd like to see how that heat spreads out over time. So, again, the point of this is just to show a couple of movies to give you an idea of what solutions to partial differential equations look like. So again, if you remember, we are just trying to find the functions which describe this motion or this diffusion of heat, and we have to find these functions that satisfy a particular governing partial differential equation. So let's jump back to the blackboard here and dive into a little bit more of the introduction of PDEs.
All right, so now might be a good time to discuss a little bit of notation. So notation with PDEs, it's very common to use partials or derivatives, right? And instead of writing partials all the time here, it's very common to use subscripts to denote these partials. So in other words, what you might see is something like, again, there's a function, let's call it u, that we're looking for. This function u had multiple independent variables like t, x, y, z, anything you'd like, right? So one quick way to denote the partial of this function with respect to one of those dependent variables is just to denote this as a subscript. So, for example, use of x is shorthand for partial of u with respect to x, right? And you might see things like u, x, y here, right? So again, this is shorthand notation for partial squared u with respect to x and y. Right? Which again, I guess is even shorter hand notation for the very verbose way of saying, take the partial of u with respect to x, right? Do that first, and then take the partial of the result here with respect to y. So again, all of these are equivalent in notation here, right? So in physics and engineering, it's very common to also see, instead of just these subscripts, you might see what's called dot and prime notation here. So what that means here is, usually we're going to see later on that the two most popular independent variables are, you have t for time and then something else for space here. So in other words, what you might see here is, you might see something trying to write down the second derivative of u with respect to the time variable. Again, usually that's t here, right? And what you're going to typically see people write here, these engineers and scientists will write something like this. You might see u dot dot here, right? So the dots on top here are basically saying this is the same thing as saying UTT here, right? Which is partial squared u with respect to t squared. So again, the dots on top are going to be used to denote a derivative with respect to time here, right? And we can contrast this with, say, the second derivative of u with respect to the spatial variable. Maybe again, in this case, let's use x as our example here, right? So the alternative notation you might see for that here is u prime prime here, which again, you could use our subscript notation we talked about earlier and say this is just uxx here, right? Which is partial u squared with respect to x squared here. So again, the dots usually denote a derivative with respect to time, and the primes denote a derivative with respect to space. Okay, with some of that notation out of the way, why don't we also talk a little bit about how about classification of PDEs? We saw earlier when we were discussing our ODEs, there are all kinds of ways you could describe an ODE. You can call it linear, you can call it nonlinear. There are all these other ways, homogeneous, non-homogeneous, what order, all that kind of stuff here, right? Well, there's a very similar lexicon here for PDEs here. So let's just go ahead and say that it looks very similar to ODEs. So if you remember earlier here, let's go ahead and write down just like a general PDE. So again, it's probably impossible to enumerate all the different possibilities here. So let's just use an example PDE with one or two independent variables and partials to kind of illustrate the fact here. So again, you said that the idea with a PDE is I'm searching for some function u. Let's make it a function of two independent variables. You know, for giggles, let's make it, how about x and y here, right? Okay. And we said the idea with the PDE is I'm searching for this function which satisfies some relationship of its derivatives. I don't know, let's make something a partial of this with respect to x here, right? Plus, maybe you leave a little bit of a gap here. How about this same function with respect to, say, y, plus, I don't know, maybe the function itself, x, y, right, is equal to some... maybe some forcing function. Let's call it dxy. Something like that here, right? Now, when we were looking at ODEs, we saw that, you know, you could also tack on coefficients here in front of all of these. And if all of these coefficients were constant, and if all of the functions, the u's here, didn't have anything crazy like squares or square roots or sine or cosines, this was what's referred to as a linear ODE. Well, it's very similar in the PDE case here, except now these coefficients are actually, they don't have to be a constant. They can be a function of x and y here, just not the function u that you're looking for itself here. So you could have an a, which is a function of x and y. You could have a b here, which is a function of x and y. And you could have a c coefficient here, which is a function of x and y here. Okay? And as long as you can write it in this format, in the sense that there are no squares or anything like that, or second or square roots or cosines here. In other words, if the degree is 1 here, and maybe we should make a note of that here. So if the degree of function u and derivatives, whoops, derivatives, I spelled that a little bit wrong. Derivatives are 1, and the coefficients are as described above, right? Then this PDE is called linear. And we're going to see there's some nice consequences of having linear PDEs. Now, the thing I want to mention here is this is the degree here. Let's just make a note here that the degree is not the order of the PDE. Remember, we talked about the order earlier. The order is how many derivatives are you taking, the order of the derivatives here. So you could have second, third, fourth, plenty of mixed partial derivatives here of order greater than 1, as long as the degree, and as long as there is no squares or cubes or you know, e's or anything like that to any of them, the degree will be 1, right? And then we can call this thing linear. Right? Okay, great. There's also another classification here within PDEs here, and then again, it involves these coefficients here. So instead of rewriting this whole thing here, maybe let's just make a little line here, and we'll note here that the other way that you could write this here is if this coefficient, you know, earlier we had a of x, y, right? This was like, let's just look at the a coefficient. If you could instead write this here of a as a function of x, y, and the function you're looking for, u of x, y. And similarly for the b of x, y and the c of x, y, these coefficients, if they could all be rewritten very slightly to be a little bit more complicated, right, like this. Well, in this case, this is no longer referred to as linear here. Linear was over here. Right? This is how you write the coefficients for a linear system. In this case, this is referred to as quasi-linear. Okay? So very small change here, right? If a system cannot, if a PDE cannot be written as linear or nonlinear or quasi-linear, it's basically referred to as nonlinear. So the last bucket here is nonlinear, right? Which is basically not linear and not quasi-linear. Then it's basically nonlinear. The last maybe adjective that we can use to describe this here is coming back to sort of the forcing function, right? This was the external input that you might have seen in an ordinary differential equation here, right? So again, you could maybe very roughly think of this as a forcing function, right? And the idea here is that if this is 0 here, right, you have what's referred to as a homogeneous one. Otherwise, it's non-homogeneous here. So maybe we're kind of running out of space here. Maybe we can just kind of keep that in the back of our head here, right? If d of x, y, if this is 0, gosh, I really don't want to rewrite this whole thing. Well, let's just state it, right? If this is 0, you have a homogeneous PDE. If it's non-zero, you have a non-homogeneous PDE, just like you had with ordinary differential equations. So, tell you what, let's look at a couple examples. I think we have enough of this notation and classification down. Let's look at a couple examples here. All right, so let's look at some famous ones here, or popular examples of PDEs. All right, so, and actually, you know what, I should probably make a note here that all of these examples here are actually linear PDEs. And actually, I think they're all second order, right, of second order. So the highest partial you're going to see here is a 2 here, okay? So just some examples. Here, example 1 here. How about something like this? Partial u squared with respect to t squared is equal to some coefficient, let's call it c squared, partial squared u with respect to x squared. Okay, so again, let's just decompose this. We see here that, again, we're looking for this function u. It's a function of 2 independent variables, time and space here. This is actually the famous one-dimensional wave equation. And we are going to be taking an in-depth look at this here in a second. Okay, so again, we see that it's linear here. It's of second order, right? You have a second partial here. And it's basically linear. Okay, let's look at another example here. How about if all you had difference here was instead of a second derivative here, on the time side, you had a single derivative here. So this could again equal c squared partial u squared partial x squared. So again, this is still a linear second order PDE here, right? Because there's a second derivative here. But we're going to see that this one little difference in partials on the time side makes a big change in the solution space here. This is what's referred to as the 1D heat equation. Okay. How about number 3 here? Another example here. This is the two-dimensional Laplace equation. You might have something like partial squared u with respect to x squared plus partial u squared with respect to y squared is 0. Okay, so this is the 2D Laplace. Okay. Another example, how about number 4 here? How about the two-dimensional Poisson, which is basically the two-dimensional Laplace with a non-zero forcing function. So it's partial squared u with respect to x squared plus partial u squared with respect to y squared is equal to some function f of x, y here. So now instead of having the 2D Laplace here, you have the 2D Poisson equation. How about another one here? Let's look at 2 more examples just so we all get the flavor here. How about the two-dimensional wave equation? So it's going to look very similar to the 1D wave equation, but there's actually going to be 2 spatial variables here. So we still have partial u with respect to t squared is equal to some coefficient, let's call it c squared, but now we've got partial u with respect to x squared plus partial u with respect to y squared. Okay, so this is now the 2D wave equation. And also, this is one that we're going to take a much greater in-depth look here later on in the discussion here. Okay, and then finally, our sixth example, how about let's look at the 3D Laplace equation. So it's partial u with respect to x squared plus partial u with respect to y squared plus partial u with respect to z squared. So what if you had three spatial variables here, and that's equal to 0 here. So this is the 3D Laplace. So again, this is what partial differential equations sort of look like. And as you can see, what they all involve here is trying to find this function u, and u has a very specific property that when you take its mixed partials with respect to whichever variable, whichever independent variable, you combine them in all the fashions that are described here, you get the left-hand side is equal to the right-hand side, right? Yeah, and maybe the only other thing to note, like we said, all of these are linear PDEs of second order, and actually example 4 is the only non-homogeneous PDE that we've written up here. Everything else is homogeneous, okay? Now, with this in mind, what we should also think about is, now that we're able to define the PDE, we can start thinking about how can we go ahead and solve the PDE. And again, I think it's so helpful to recall our discussion on ordinary differential equations. You remember here with ODEs, if someone just gave you an ODE and said solve it, that's actually yields an infinite amount of solutions. And that's similar in many of these PDE cases here, in the sense that many dissimilar functions will solve these equations of motion, or these partial differential equations. So for example, let's go ahead and how about consider the 2D Laplace. Okay, so the 2D Laplace equation, what do we say that was? That is partial u squared with respect to x squared plus partial u squared with respect to y squared is equal to 0. So this actually yields a family of solutions. So for example, I can just pull out of thin air a bunch of these actual u's that would solve this. So for example, let's go ahead and try, here's solution 1. U of xy is equal to x squared minus y squared. How about a second example here? U2 of xy is equal to e to the x cosine of y. That looks nothing like the first set of solutions. All right, how about u3 here? u3 of xy. How about this? How about natural log of x squared plus y squared? Why don't we run over to Mathematica and verify that actually all three of these very dissimilar functions here will solve the 2D Laplace equation.
All right, so here we are with Mathematica. Let's go ahead and just quickly, how about define these functions that we talked about just now on the board here. So I think we had a u1 of x and y here. This was x squared minus y squared was our candidate here. And then I think we had two other ones, right? A u2 and a u3. And u2 we claimed was e to the x cosine of, whoops, that should be an x, right? X cosine of y. And then finally, u3 was natural log, log of x squared plus y squared, right? Okay, that's our functions, and what we claimed is all of these would solve the 2D Laplace, so let's go ahead and how about define the 2D Laplacian operator, right? That was what we needed here. So that was our del 2D, let's say. And let's say you pass this thing a function u here. And what this thing does, and I'll actually use the set delay. So colon equals, what it did was it took the function u here, and it took its derivative with respect to x twice. And then what it did here was added that to the function's derivative with respect to y twice here, right? So what this is here is this is effectively uxx plus uyy here. All right, so I'll shift enter that. I don't need a semicolon there because I use the set delay operator. And now let's go ahead and just go ahead and do a check here. So let's verify that this solves the PDE here. So what that meant here is I just need to pass in del 2D. Let's give it these three functions. So u1 of x and y here, right? So what this should happen, this should do is once I shift enter this, let's cross our fingers and hope this equals 0. Yep, that worked here. Let's do the same for the other two functions and see if this works here. So u2 and u2 and u3 Shift Enter. Oh, okay, it worked for 2, but 3 here. I think 3 just needs a little bit of persuasion here. I think those actually are the same thing here, but if I go ahead and let's say / simplify and give Mathematica a little bit of chance to clean that up, and yep, there we go. So all of these satisfy the 2D Laplace. So as we see here, this family of dissimilar functions for this PDE are all able to solve the governing PDE. So I guess the natural question is, how do we narrow down the solution space here so we can get a single or a unique solution?
All right, so we saw that, yeah, these are dissimilar families of functions, but they all solve the PDE here. So in order to actually reduce the solution space here, so in order to reduce solution space, we're going to see that we're going to need to apply, just like we did in ordinary differential equations, we'll have to apply some initial conditions, or let's call them ICs, as well as in many cases we saw earlier that an initial condition, just by the name of it, it seems to imply initial time here, right? So we need to fix what happens in the temporal variable, but we're also going to have to apply probably what are called boundary conditions. Or we'll call them BCs. So hopefully, if we now have the original PDE as well as some initial conditions and some boundary conditions, that will allow us to choke down the solution space and get something more like a unique situation here. Okay, so with that, that actually brings us to an interesting discussion here that we saw that, okay, a PDE might have multiple solutions here. One question you might ask yourself is, well, if I find myself 2 solutions to a PDE, could I generate a third solution based on that those 2 solutions that I already found? All right. So let's write down actually one of the key theorems here of PDEs that deals exactly with this case. So this is, in fact, it's so important that sometimes this is referred to as the fundamental theorem, which is basically the idea of superposition. Okay? So what this states here is that, again, like we said, if U1 and U2 are solutions of a linear homogeneous, well, that's actually a little bit key. So this doesn't work for all PDEs here, but if you have a linear homogeneous PDE, so U1 and U2 are solutions to this PDE, let's say in some region R of the solution space, then you know what you could do here is you could take U1 and you could add it to U2. In fact, you can even jam on coefficients in front of these, C1 and C2. And this, let's call it maybe U here, right? It's a linear combination of U1 and U2. If this is the case, then you know what? U is actually also a solution. So this, again, should be very similar to, and ringing some bells to when we discussed ordinary differential equations, where we did a very similar thing where we added up multiple solutions and created a third solution. And you know what? Why stop at 3, right? Maybe you add 3, 4, 5, 6, 7, 8 different, infinite number of solutions to create yet another solution. So in other words, you could go ahead and say, you know what? If I have, let's say, UN, and I'll go tack on a coefficient Cn, and I'm going to sum this thing up from n equals 1 to, I don't know, big N. So I have big N solutions to my PDE. I can just add them together to obtain yet another PDE. Okay, I want to remember this here because we're going to come back and discuss this within the context of Fourier analysis when we start trying to build up general solutions to arbitrary initial conditions and boundary conditions. We are going to be using this fact extensively down the road here. So again, hopefully this is nothing too earth-shattering right now. We've seen things like this before here. In fact, we could even jump back to Mathematica and verify that this works here. So why don't we do that right now? Let's use the exact same examples we did earlier and just start adding up linear combinations of them and verifying that they still solve the PDE.
All right, so we're back at that same notebook. So let's go ahead and apply the fundamental theorem. In other words, we are going to apply superposition to start creating additional solutions. So for example, I can make a U4 of x and y, right, which is going to be, I don't know, a C1 times U1 of x and y plus a C2 times a U2 of x and y. And again, you know what? I don't even need to pick C1 and C2 because theoretically this should work for any C1 and C2 as long as they're constant here. So let's go ahead and define this as my fourth solution, and let's run it through this operator again. So del 2D, which is our 2D Laplacian of U4 of x and y. I'll pass this in, and look at that. It's still 0. So it sure looks like superposition works, and you know what? We can even come back here and get a little bit more complicated, right? C3 times U3 of x and y. Let's add those all together. So now I've got something really complicated. Let's try this again. And again, yeah, we'll probably need to simplify this thing a little bit. But you know what? It's still 0. So here we go. Superposition held for this case, and actually it should hold for any linear homogeneous partial differential equation.
All right, so this is all very exciting. We saw that if I have some solutions of a PDE, I can easily generate other solutions based on those, and I can do this as many times as I want. However, here's the rub, right? Is how did I get those solutions to the PDE in the first place? And that's where the whole art and the elegance comes in here, right? In general, PDEs are they're a difficult beast here, right? If you have a general arbitrary partial differential equation, it is very difficult to solve, and a lot of times there won't be a general solution. However, if the system or the PDE is simple enough, you might be able to solve for a general solution. So I want to take a look at a very simple example of a reasonable, easy to solve PDE and how you might be able to do this analytically here. So let's talk about, how about an example here of a simple PDE. And how can I go ahead and solve this analytically? So let's go ahead and consider a PDE. So the PDE I'd like to look at here is uxy is equal to minus ux here. So again, recall, this is shorthand notation for I'm looking for a function u that satisfies partial u with respect to xy here is equal to the negative partial of the function u with respect to x here, right? That's all the same thing. So I'm looking for, the goal here is find this function u of x and y here, which satisfies this PDE here, right? I got to be able to take its partial derivative with respect to x and then with respect to y, and that better equal the same thing if I took the partial of that thing with respect to x and then stuck a minus sign in front of this here, right? Okay, how are we going to go ahead and solve this here? This PDE is simple enough that we might be able to do this using analytical techniques. Okay. So the first thing I want to do here is let's go ahead and assume that we found u. So assume we have this function u. Then we're done here. Well, let's go make sure it satisfies this PDE here. So the first thing I want to do here is let's take the derivative with respect to x. So let's go ahead and do ux. And let's say that what this kicks out is this generates some function. Let's call it p here. So this is a function obtained by taking partial u with respect to x here, right? U is some complicated function of both x and y. You take its partial, you get something a little bit less complicated, but it's still a function of x and y, okay? All right, let's go ahead and now take the derivative of both sides here with respect to y here. So let's write that down. So take derivative with respect to y next here. So in other words, I'm going to go ahead and calculate partial of ux with respect to y is equal to the partial with respect to y of p. Something like that here, right? So again, left-hand side, shorthand notation, I could write this thing as uxy, right? That's the same thing here. And I could write shorthand notation of this as just p sub y, right? Okay, so if you recall here, what is the whole point of what does uxy have to satisfy? It has to satisfy this here, right? So let's make a note here. So recall here that we said u of xy has got to equal negative ux, right? So let's substitute negative ux over here on the left-hand side, right? Because it theoretically needs to be the exact same thing here, right? So we end up with the left-hand side becomes minus ux is equal to p sub y. Okay? So if you recall earlier here, what we said here is that actually u of x is equal to p here, right? So that's what we said up here. So again, let's make a little note here and recall from previous discussion here that we said ux is equal to p, right? So again, let's go ahead and substitute this in on the left-hand side. So I could write here, how about minus p is equal to negative p sub y, right? Okay, great. So I could also rewrite this, how about as, let's move everything to one side, I could rewrite this as p sub y over p is equal to negative 1, right? Same thing. Okay, great. Now let's go ahead and integrate both sides with respect to y here. So let's write that down. So int with respect to y of both sides here, right? So what I'm doing here is I've got py over p. I'm going to integrate this side with respect to y. This has got to equal negative 1 integrated with respect to y, right? Okay, if you remember here, this is basically a natural log, right? So we end up with, what is the left-hand side? This is natural log of p here is equal to, what do we end up with over here? That's just, oh, actually, we better be a little careful. So this is minus y here, right? Plus some constant of integration. Actually, you know what? Both of these things would have kicked out some constant of integration. Let's move both constant of integrations over here, right? Plus, maybe let's call it a c here, tilde here, right? So it's both of those constant of integrations kicked over here. And the other thing that's interesting about this constant of integration, right, it's not just a constant. Because we're integrating with respect to y, this thing could actually be any function as long as it's only a function of x here, right? So it's not a constant, it can be a function of x here. So I'm going to denote it like such so we keep that in the back of our head, right? Okay, let's raise both of these things to the e, right? So to simplify this, so let's go e to the natural log of p is equal to the e to the negative y plus c tilde x, right? Okay, so simplifying this thing a little bit, what do we end up with? We get p on the left side here, and then over here we end up with, you could write this whole thing as e to the minus y times e to the c tilde x here, right? And okay, let's look at this little c, e to the c tilde x. This is just, again, some arbitrary function of of x here, right? So let's go ahead and just rename this so we don't have to keep rewriting this whole thing. Let's just rename this whole thing, how about c of x, right? It's just some other arbitrary function of x, right? All right, so what do we've got here? Now we've got p here is equal to the e to the negative y times c of x, right? Now, if you remember again, right, we said that p is equal to u sub x, right? So let's put that in on the left-hand side, right? This is what we said way back in the beginning. Let's put this in on the left-hand side here. So what do we end up with? We end up with u sub x is equal to, I guess I'll just switch the order of this to make the look a little bit nicer. Let's go c to the x, e to the negative y, right? Okay, great. Now let's go actually the other side of the board here. Let's integrate both sides with respect to x. So now int with respect to x, right? Both of these sides. So I'm going to go integrate u sub x dx here. This has got to equal integral of c of x times e to the negative y dx, like such, right? All right, so left-hand side, that's pretty obvious here, what we end up with here. This is just u. Great, that's what I'm looking for. Now, the right-hand side, let's take a look at this a little bit. E to the y, luckily that is not a function of x here, so I can pull that out of the integral, right? So let's get e to the negative y outside here. And now we end up with integral of c to the x dx, right? Okay, perfect. This thing here, right, this integral, we can do the exact same trick we did earlier. We could say, you know, this is just some integral, some arbitrary function of x, so it's going to be some other function of x here. plus a constant of integration, and that constant of integration can be anything as long as it's just a function of y here, right? So in other words, let's rewrite this like such, e to the negative y, and then inside here, this is going to be f of x here, right? So f of x is just the whatever happens when you integrate this function of x with respect to x, you get some other function. Let's just call this thing f for now, right? Plus something else, some constant of integration, let's call it r, but this constant of integration r can be a function of y here, right? Because of the way we integrate it. Okay, perfect. Okay. You know what? Let's just distribute this thing through here. So we end up with e to the minus y f of x plus e to the minus y r of y. Okay? And again, you look at this thing over here. This is just some crazy function of y here, right? So you know what? Let's just call this thing, how about, what did I end up using? A g sub y. It's just some other function, right? Okay, great. So at the end of the day, what we end up with here is this function u of x and y here, right, that we're looking for. It's just e to the negative y times some function of x plus some function of y, right? So box this up. So this is really fascinating. If you look at this here, it's basically saying any function that is going to solve that PDE that we started out with, it really can be anything you want as long as you have some function, you know, your function f is just a function of x. You then have to multiply it by e to the y in the front. Then you have to add it to whatever the heck function you want as long as it's only a function of y here, right? So, for example, let's just choose a couple of random functions just to see if this thing works, right? So, I don't know, let's pick some arbitrary functions. Let's make a table here. So f of x and then g sub y. So let's do a couple of cases. How about f of x? What if you pick something like, I don't know, cosine of x here, right? And then g sub y, this could be something like y squared. Again, the concept here is everything in this column, the f's, it can only be a function of x. These things, they can only be a function of y here, right? And then, I don't know, let's look at another test case. I think I'm going to look at, how about natural log of x here? And then how about tangent of y squared? That'll apparently work. How about something even crazier? How about, I don't know, x cubed plus 3x plus 1 over cotangent natural log of x. Something like that, right? Again, something crazy, but it's just a function of x. Over here on the y side, I don't know, something nuts also. Y squared e to the y cubed, or to the fourth, y to the fourth. You know what? Okay, all of these should work here. So what we want to do now is go ahead and compose this u of xy using the expression we had earlier, right? You take whatever's in this first column, you multiply by e to the y, and you add it to the second column here. And let's go ahead and show that this will basically solve our original differential equation here, which we said was uxy is equal to negative ux. Okay, and that's a lot of boring busy work, so I don't think I want to do this here on the board. So let's run over to Mathematica and see if this works.
All right, so here we are over in Mathematica again. So let's go ahead and first, how about choose some of these f of x and g sub y functions that we just talked about here, and use that to compose this solution. Maybe let's call it u1 is x of y. Let's do this all in one go here, right? We said that, all right, the general solution of this was e to the minus y times f of x plus gy, right? And now let's go ahead and just use one of the f and the g's that we discussed. So let's slash dot and say replace anywhere you see an f of x. Let's use the first example of how about cosine of x, and then gy we said was going to be y squared here, right? So here's u1. That's my first candidate function. Let's go ahead and make sure that this satisfies. So we're going to verify that this satisfies. What was our PDE? I think it was uxy is equal to minus ux. Did I get that right? I think that's what our PDE was. So what I need to do here is, all right, let's do the left-hand side. Let's take the derivative of the function here, my candidate solution, xy. I'm going to take the derivative of this here first with respect to x, and then with respect to y here, right? So here's the left-hand side here, right? This is uxy here. Okay, and I really better make sure that this equals negative the partial derivative of u1 of xy, my solution, with respect to x here, right? Great, so here we go. This should check if the left-hand side equals right-hand side, and hey, look at that, it's true. That ended up working. Let's go back up here and choose a couple of more complicated examples that we had earlier. So let's make a u2 and a u3. So I think our replacements here for f and x, we tried something a little bit more complicated for the second one. I think we said this was natural log of x, and then I think we said tangent of y squared, something like that. And then for our third case, this was our most complicated thing. I think we said f was going to be x cubed plus 3x plus 1 over cotangent natural log of x. Something like that, something really complicated. And then y here was going to be y squared e to the y4, right? Something like that. So here's our bunch of complicated candidate solutions. And again, let's just verify that these work. So what that meant is just plugging it into the original governing partial differential equation. So I'll plug all three of those in here and shift enter this, and look at that. True, true, true. All of these work here, right? So in this case, we were able to find an analytical solution to this general partial differential equation here, and that's really satisfying here. Although we're not going to be able to do this in general here. So we're going to require more formal methods to solve some of these additional PDEs. So one popular technique is actually to treat an ODE like a PDE. And we're going to investigate this in our next lecture.
All right, so we saw that this actually works, and while this solution method, while elegant, I'm sure you can kind of think to yourself that, you know what, this isn't really practical nor tractable, especially for some more complicated partial differential equations here. It happened to work nicely in this case, but in general, this might be a difficult technique. So, with that being said, I think this is a good spot to stop this first video lecture here. And this sets the stage nicely for our next topic here, namely, how can we come up with a more formal technique to solve some of these linear partial differential equations? So I hope you'll join us at our next video, where we are going to start discussing the one-dimensional wave equation, and we'll look at techniques such as separation of variables to go ahead and solve more complicated PDEs. So, with that being said, I hope you enjoyed the video. If so, please subscribe to the channel here, because we're going to be having a ton more of these discussions here related to partial differential equations and other math topics in the future. So I hope to catch you at one of those future videos. Thanks so much. I'll talk to you later. Bye.